Okay, we're going to finish up some of our thermo problems. This is number 59 from chapter 16, and we're looking at the question, considering this reaction 2NO gas is in equilibrium with N2O4 gas, and then for each of the following mixtures, and they give us three different pressure scenarios, so I'll just write down for part A, the pressure of the NO2 is equal to the pressure of the N2O4 is equal to 1.0 atm. And we're looking for predict the direction in which the reaction will shift to reach equilibrium. Okay, so this delta G has, when we talk about Gibbs free energy, if delta G is negative, that means that the reaction is spontaneous and will proceed to the right. Now, when we adjust for this ln of Q, what happens is, as our pressures change, so as we shift to the right and these pressures change because the reaction is making more N2O4, so my N2O4 would go up and my NO2 would go down. As these pressures change, it's affecting the Q value. And if the Q value changes, then my delta G is going to change. So remember, when delta G is negative, it's spontaneous, will go to the right. Shifts to the right. If delta G is positive, it's not spontaneous, and when it's not the standard state delta G, that means we're going to shift to the left. And when delta G is equal to 0, you're at equilibrium. Okay? And so when delta G equals 0, that means that my delta G standard state is going to equal negative RT ln Q. So when my Q value makes this equal to my delta G at standard state, that means that I'm at equilibrium, because when these two are equal and opposite, I'm at equilibrium. I have a delta G of 0, and that means that I would be at equilibrium. Okay, so we're going to look at the first one. So we're going to just start to plug in here. So the first thing I need is I need my delta G at standard state. So I'm going to look in Appendix 4. And in Appendix 4, I can get the numbers to plug in here because I know that it's the sum of the NP delta H products, delta G products, minus the sum of the NR delta G reactants. And since there's only one of each, I looked up the values, and it comes out to be 98 minus 2 times 52, which is, this comes out to be 98 minus 104, which is negative 6 kilojoules per mole. So that's the delta G of standard state. And so we're just going to write that in joules per mole because we know we're going to need it in joules per mole as well. Okay, so now for part A, so that's for all of the parts. So for part A, it says, okay, well, let's compare and let's see what happens. Delta G is equal to delta G standard plus RT ln Q. And we're going to put our Q value in. So Q is going to equal the pressure of the N2O4 over the pressure of the NO squared, because there's a 2 in front of that. And so if I do the Q for these ones, it's 1 over 1 squared, which is 1. And so delta G is going to equal negative 6,000 plus 8.314 times, we're at 298 Kelvin, times ln of 1, but we know ln of 1 is 0, so this whole piece, that goes to 0, and so delta G is equal to negative 6,000. Since it's negative, it's spontaneous to the right, this reaction will proceed to the right, so we say that it shifts right. Okay, for part B, it says the pressure of the NO2 is equal to 0.21, and the pressure of the N2O4 is equal to 0.5. So I'm just going to calculate Q really quick. Q is P of N2O4 over P of NO2 squared. So 0.5 over 0.21 squared. And when we do that, let's get my calculator, we get 0.5 divided by 0.21 squared, and we get 11.3. Let's see. is 2 sig figs, so we're going to call that 11. Okay, and then we're going to calculate our delta G, which is equal to negative 6,000 joules per mole plus 8.314 times 298 times ln of 11. Okay, and let's see what we get for our delta G. So negative 6,000. Actually, you know what I'm going to do? I'm just going to check what this number comes out to be. 8.314 times 298 times ln of 11. Oops, I did E, sorry. ln of 11. And we get, this comes out to be 5940 and negative 6,000. This probably, if I had kept the 11.3, so let's see, ln of 11.3 times 298 times 8.314. And we get 6,000. So these are approximately equal, but if we did it out, we would get negative 60, and so delta G is negative. Perhaps it would shift to the right. That would say shifts to the right. If I left a couple more sig figs on this, I think you might find out that delta G is approximately 0, and then you would be at equilibrium. Okay, but that's how you do that. You compare and see what your delta G comes out to be. And then for part C, we have pressure of NO2 is equal to 0.29, pressure of N2O4 is equal to 1.6, and so Q is equal to 1.6 over 0.29 squared. And when I do that, 1.6 divided by 0.29 squared, we get 19.02. And so our delta G is equal to negative 6,000 plus 8.314 times 298 times ln of 19.02. And this is going to come out to be a positive number. And when delta G is positive, it's not spontaneous. In fact, it will proceed to the left if we have an equilibrium situation. So this is going to shift to the left. Okay, and that's how you relate the delta G. Oops, sorry, I'm off the page a little bit. That's how you relate the delta G to the K value and the Q value. Okay, let's look at 61. So number 61 says consider the following reaction. We have the same reaction. 2NO2 is in equilibrium with N2O4. Both of these being gases. And it says the values of delta H are negative 58.03 kilojoules per mole. And delta S at standard state, both of these, is negative 176.6 joules per mole Kelvin. And it says calculate K. So we're trying to calculate K. Assuming delta H and delta S are temperature independent, estimate the K at 100 degrees Celsius. So we're going to calculate K at 25 degrees Celsius first. Okay. So when you're talking about the equilibrium position, and that's K, not Q, right? Then at equilibrium, the delta G, not the standard state delta G, but the regular delta G, the full delta G, the Gibbs free energy, is equal to 0. And since the formula is delta G standard state plus RT ln of Q, well, this means at equilibrium, and at equilibrium, Q is equal to K, and so this gets rewritten that at equilibrium, 0 is equal to delta G standard state plus RT ln K. So if I can find delta G standard state, I can find K. And I can find delta G standard state because I know delta G is equal to delta H minus T delta S. And I'm given delta H, so I'm going to put delta H in joules because delta S is in joules. So my T is 298 Kelvin, and my delta S is in joules, negative 176.6. And so when I do that, I get negative 58,030. And then let me get my calculator. We'll do 298 times 176.6. And I get plus 52 And let's see, 3 sig figs, so we have to round this to 6, 0, 0. And when I add those two, negative 58030 plus 52600, I have to round to, let's see, 1, 2 to the hundredths place. So this would be negative 5,400 joules per mole. That's delta G at standard state. So spontaneous, right? So what's K then? So if I plug the delta G in here, I would say 0 equals negative 5,400 plus 8.314. We're still at the 298 Kelvin times K. So I'm going to add the 5,400 to the other side. And I get 5,400 equals, let me multiply 8.314 and 298, 8.314 times 298, and we get 243 sig figs, so 2480 ln of k, sorry, that should say ln of k, times the ln of k. Now divide both sides by 2480, and you get k is equal to 5,400 divided by 2480, and I get k is equal, sorry, I did again, ln of k. ln of k is equal to 2.18. Now, how do I get the k? Well, remember, ln means log base e, so e raised to that number equals k. So k is equal to e raised to the 2.18. And so we're going to take our calculator and do e to the x, e raised to the 2.18, and we get k is equal to 8.85. And that's how you do that. Now, based on some rounding here, the answer key in the book might be off a little bit, and that's okay as long as you're doing the work correctly. I'm not going to worry about the sig figs. Second, let's take a look at the second part of this problem. It says, let's assume that the temperature is doesn't change, right? It says, assuming delta H and delta S are temperature independent. So delta H and delta S at standard state are temperature independent. So that does not mean that the temperature doesn't change. It means that these two values don't change when the temperature changes. So I misspoke there. So this is part B. So if delta H and delta S are temperature independent, it says find K at 100 degrees. Okay, so this one up here, this was 25 degrees. Now remember when we did equilibrium, if we increase the temperature, the K can change. If the K goes up, then we look at, was this an endothermic or an exothermic reaction? So if we increase the temperature, we can figure out what kind of reaction is dependent on what K does. And so this is another way to actually figure that out. So we're going to find delta G again, because delta G changes with temperature. Delta G is equal to delta H minus T delta S. But now my T is going to be 373 Kelvin. So we're going to still put in our same numbers from what was given in the earlier part. I don't know if I can see both on here, right? So that's up here, 58.03. This is what was given earlier. So we're going to put in negative 58.030 joules minus 373 times negative 176.6. Okay, so our delta G is different in this problem. So we have negative 5803030, and then a minus times a minus is a plus, 373 times 176.6. And we get delta G is equal to positive 7,800, because let's see, I guess I can actually go down to the tens place here. So 7,841. So 7,840. And then that, and that's the standard state. And so then we're going to go back to our equation that was here and say, all right, well, at equilibrium, the delta G is 0. And so we say 0 is equal to delta G at standard state plus RT ln K. And a lot of times you see this written as delta G is equal to negative RT ln K. This is at equilibrium, right? Because if I just subtract the RT ln K to the other side, that's what it equals. And so we're trying to find K, so we're going to say 7,840 equals negative 8.314 times 373 times the ln of K. And I'm going to divide 7,840 divided by 8.314 divided by 373. And we get ln K is equal to 2.53. And so E raised to that equals K. So K is equal to E raised to the 2.53, which is equal to let's see. Oh, it should be negative. So this should be a negative number because when I divided, that should have come out to be negative. So let me try that again. E raised to the negative 2.53. And we get 0.080. Okay. I gotta double check here. 58. I'm just gonna double check this number because it looks like I thought it was going to be off by a factor of 10. 58030 plus 373 times 176.6. Okay, divided by 8.314 divided by 373. Okay, 0.080, and that would be your K value. Okay, so that's 61. Let's take a look at 63. We have two more. So number 63 is combining two equations. We have H2 gas plus O2 gas is in equilibrium with H2O2 gas, and K is equal to 2.3 times 10 to the 6 at 600 Kelvin. And then we have 2H2 gas plus O2 gas is in equilibrium with 2H2O gas, and that K is equal to 1.8 times 10 to the 37 at 600 Kelvin. And the question is, find delta G at standard conditions for the equation H2O gas plus 1/2 O2 gas is in equilibrium with H2O2 gas at 600 Kelvin. Okay, so this definitely looks like a Hess's law type adding and subtracting of equations. So let's just look and rewrite these equations and remember how we deal with the K's when we do this. Okay, I want the H2O on the left. So this first one, I'm going to reverse it. And when I reverse it, I get 2H2O. I'm going to do this in two steps so you see what happens. Is in equilibrium with 2H2 gas and O2 gas. Now, when I reverse, I reciprocal the K. So my K for this is 1 over 1.8 times 10 to the 37. Now, I only want one H2O when I end up, right? Because this is the equation I'm trying to get. So if I only want one H2O, then I'm going to multiply that by 1/2. So I get H2O gas is in equilibrium with H2 gas plus 1/2 O2 gas. And when I multiply that in half, the new K is the square root of that other K, 1 over 1.8 times 10 to the 37. And then, if you can see it, we just bring this top one down, and that's going to be enough because we're going to get the equation we want. H2 gas plus O2 gas is in equilibrium with H2O2 gas. So what cancels out if I'm adding these two equations? Okay, and I'll bring down that other K because I didn't change that first equation, 2.3 times 10 to the 6. That's from above, right? So this H2 is going to cancel this H2. This H2O remains, so I get H2O gas. The H2O2 remains, H2O2 gas. And I have one O2 here, and I have 1/2 of an O2 on the other side. So that leaves me with a half of an O2 gas here. Okay, so when I add these two reactions, I get the one that I wanted. When I add two reactions, I multiply the K's. So the K for this is going to be the square root of 1 over 1.8 times 10 to the 37 times 2.3 times 10 to the 6. And when you do that in your calculator, you should get that K is equal to 5.4 times 10 to the minus 13. Okay, so now we're trying to find delta G for this reaction. Well, delta G, right, the question for 63 says, find delta G at standard state, and delta G at standard state is equal to negative RT ln of K. So negative 8.314 times the temperature, 600 Kelvin, because we're already in Kelvin, times the natural log of 5.4 times 10 to the minus 13. So we're going to put that into our calculator. Negative 8.314 times 600 times the natural log of 5.4 times 10 to the minus 13. And we get, let's see. Oh, I did it again. I did the E value. Try that again. I always do the second button on it. Negative 8.314 times 600 times natural log. I tend to do the second by accident. 5.4 times 10 to the negative 13. And we get delta G, standard conditions, is equal to 140,908 joules per mole, which is equal to 141 kilojoules per mole. Okay, and then the last one, we have consider the following reaction at 800 Kelvin. So this one here was 63. I'll just label them. And 65. Consider the following reaction at 800 Kelvin. And we have N2 gas plus 3 F2 gas makes 2 NF3 gas. At equilibrium, a mixture contains pressure of N2 is equal to 0.021. Pressure of F2 is equal to 0.063. Pressure of NF3 is equal to 0.48. And it says calculate delta G standard. Find delta G at standard state. Well, we know delta G at standard state is equal to negative RT ln of K. And we're given the pressures at equilibrium. And so I can find the K value. So let's just do that separate. So K, since these are the pressures at K, is going to equal pressure of NF3 squared, because that's a 2, over pressure of N2 times pressure of F2 cubed. And so when I plug those in, I get 0.48 squared over 0.021 times 0.063 cubed. So let's get the K value. So we have 0.48 squared divided by 0.21 times 0.063 raised to the 3. And we get K is equal to 4,387, but since there's only 2 sig figs, that has to go to 4,400. That's our K value. And now we can say what delta G is. Delta G at standard state is negative 8.314 joules per mole Kelvin times the temperature in Kelvin. And in this problem, they told us the temperature was 800 Kelvin times the natural log of 4,400. And so if I plug that in, we get negative 8.314 times 800 times the natural log of 4,400. And so we get delta G is equal to negative 55,799 joules per mole, which is the same as negative 55.8 kilojoules per mole. Okay, and I hope that helps with some of the thermo problems.